I worked with Brian from 1985 to 1990. I was a PhD student and a research assistant at that time. So let's start a bit more quickly than I thought, but thank you very much to Lionel for inviting me here and to all Brian's family for arranging this symposium. I think something that several people have talked about is how Brian took inspiration from nature in arriving at his inventions, particularly vortices. We just heard a lot about vortices, vortex mixing. Just simple ideas, really, that you can observe in everyday life, but are very, very effective in the case of Brian, enhancing the performance of artificial organs. So after I worked with Brian, I didn't directly go on to apply that work at the time. I went to work in different fields, mainly renewable energies. But then I became interested in applying renewable energies to water treatment and desalination. So it's actually later on in my career that I came back to thinking about the work that I did with Brian. So, interestingly, I now found that the ideas that Brian worked on are actually, even though, decades have gone by, are very, very important today, I believe, and actually have, more to be done, much more to be done than has already been done. So, as I said, today I work particularly in the field of desalination. So desalination, the process of separating fresh water from seawater or saline groundwater in order to provide drinking water or even water for agriculture. So today, 4% of the world's population rely on desalination for drinking water. Countries like Saudi Arabia, many Gulf countries, you wouldn't be there with those huge populations if they didn't have desalination. So desalination today is mostly based on membrane processes. So that's the connection I want to make with the work with Brian. So as I said, I worked at 43 Banbury Road. Here we have it again, and this is a photo from the time. So I think this shows Lionel that it indeed hasn't changed very much, but maybe, I don't know if all those trees are still there, but there was very nice colours in the autumn against the red bricks of the house. So I do remember a lot about the details of the house and the sort of big heavy door at the front and the way it closed and opened, and all the kind of little rooms inside with all the labs. It was a very nice place to work in that sense. As we've heard, the work at that time was, it was on lots of topics, but Brian's work was quite focused on artificial organs like oxygenators then, plasmapheresis devices. I think there was work going on dialysis before I joined, plus all the work that Lionel described. There was also work I remember on separating, using fluid mechanic effects to separate sickle cell anemia cells, which have a different shape, mostly exploiting the interaction between the fluid mechanics and the movement of the blood cells. So I too, was very much interested, became interested, or the starting point for my work was the application of vortex mixing. So vortex mixing as a way to overcome concentration polarization. So as Ian just explained, concentration polarization is the process that defeats the performance of membrane mass transfer devices like oxygenators, where the oxygen would build up at the wall of the membrane and not readily transfer into the fluid. Or in my case, I was looking at separation of blood proteins. So the objective was to be able to selectively separate immunoglobulins from the blood. Immunoglobulins in certain conditions can cause autoimmune diseases where the body starts to kind of attack itself. So we're looking at ways of fractionating blood proteins. So concentration polarization then again limits the performance of the process because it's slightly different in this case. You're trying to get oxygen into the blood. Here you're trying to get liquid to come out of the blood. But as you try to get liquid to come out of the blood, the retained species concentrate against the membrane, which forms an impermeable barrier and build up a gel layer. So it's the rate of diffusion or mass transfer of the proteins back into the fluid that limits the performance of the device. So vortex mixing could be applied to that as well as to oxygenators. So I actually found, looking in the literature, quite a nice definition of vortex mixing, which I thought I'd read out. It says, it is a process in which a strong reversing flow component is superimposed on a continuous flow across a corrugated surface to produce vortex formation and ejection. So I thought it was just nice to have that concise definition. So one aspect of the work was to do with applying vortex mixing to plasma separation, and then that kind of progressed into a different aspect of the work where we were looking at adsorbents for plasma fractionation. So I didn't manage to find so many nice photos as Ian had. Unfortunately, I didn't seem to take quite so many photos of my equipment, or at least I couldn't find them in time for this presentation. I do remember using the very same computer that Lionel showed, this IBM, which I think was the only computer in the building, apart from the PDP-11, which had been decommissioned by then. So it was quite amazing that over a period of 4 or 5 years, you had a whole lab just working with just one PC, which is a very coveted thing, with I think maybe 120 kilobytes of memory or 250, quite limited. And so that was used to control these devices. So the innovation was the development of membranes which could absorb proteins selectively from the blood. That was something that Malgosia, worked on and developed the biochemistry of it. And my job was to work on the sort of optimization, performance, and understanding the physical mechanisms involved. So as I said, I didn't go directly from working with Brian onto working on medical topics. I went to work on renewable energy and then applications of renewable energy in desalination in particular. So during the 1980s, desalination was a relatively small industry, and what happened in the 1990s was they invented much better membranes for desalination. So desalination uses reverse osmosis membranes that are similar in principle to the ultrafiltration and microfiltration membranes that are useful in the filtration processes that we've just described, but they're selected to water and reject salt. And the membranes that could really do that effectively were developed in the 1990s. Before that, desalination was done more by thermal processes. So during the 1990s, the new membranes came online. The demand for water, and particularly in the Gulf countries, increased a great deal. So the global capacity of desalination has gone up about 10 times since then. So today there's about 100 million cubic meters of water produced by desalination every day, and that amount continues to increase. So alongside that, there's a big amount of research going on in desalination. The fundamental driver is water scarcity. So it's something that's very much in the news these days as we hear about the drought in South Africa, water scarcity in Cape Town. So it's all driven by essentially population growth across the world's hot, arid regions. So the red areas show countries where water is particularly scarce. So water scarcity is defined as any availability of renewable water resources below about 1,700 cubic meters per person per year. So that sounds like a lot, 1,700 cubic meters per year per person. We don't drink that much, but the reason is that most water is used for agriculture. So worldwide, about 70% of managed water is used for agriculture, and in arid countries it could be 90% or even more. So there's a big link between water and agriculture and food. There's a big link between desalination to provide water and energy. So there's a link between energy and water and food, and if you like, desalination lies at the middle of it. So a lot of the research today is about reducing the energy requirement of desalination. So what I wanted to highlight in describing the research work and how it followed on in some ways from what I did with Brian was the whole business of how you would like to minimize the energy consumption of desalination. After all, in artificial organs, the energy consumption of the device isn't really a big concern. That's a lesser concern. But in desalination, the energy consumption is the big thing, really. So there's a number of projects going on, globally on desalination, a number of research projects, and some research projects that I've been involved in or currently am involved in. And a lot of these tend to arise in the Middle East because that's the area where it's most needed, although desalination is also very important in India, in the whole Indian subcontinent, in lots of parts of Africa. So this particular map that was prepared by some of my students highlights particular water scarcity problems in the Middle East and the lack of aquifers there. So I said a moment ago about how you'd like to have 1,700 cubic meters of water per person per year, roughly speaking, to say that water is not scarce, but yet in many countries it's less than 100. So countries including the Yemen, Saudi Arabia, Palestinian territories, Jordan, Oman, and United Arab Emirates all have less than 100. So it's more than a factor of 10 less than you'd like to have. And that's, if you like, tolerable for countries that are wealthy and can afford the desalination technology and its energy consumption. But for countries like the Yemen or Palestinian territories, Jordan, it's not really affordable. So therein lies a big problem, which is gradually getting worse due to the big growth of population in the region. So that brings me on to a current project that I'd like to highlight. So this is a project sponsored by the British Council and the Davies-sponsored Trust, which is about, it's a trilateral project between UK, Israel and Palestinian stakeholders. So it's about solar power desalination for the Jordan Valley. So what we're doing is we're bringing together groups of students from Palestine, Jordan, Israel, UK and other countries as well, to work on this shared problem of water scarcity in the Middle East. So obviously, it's a politically contentious area, but the project is just about giving students the chance to work together to work on a common challenge. It's not about the politics of the situation, or because we're aware of that. This diagram shows exactly why it is an important issue, and an issue for water security and if you like, military security in the Middle East. It's the fact that the national boundaries or the territorial boundaries straddle aquifers in the region. So the Jordan Valley lies over what's called the Western Aquifer, then you've got the Eastern Aquifer, then you've got the Western Aquifer and the Coastal Aquifer. So all these aquifers straddle these political boundaries, and effectively different peoples, the Jordanians, the Palestinians and the Israelis, are all withdrawing water from the same aquifers. So you can either think that's a cause for conflict, or it's also a cause for collaboration and cooperation. So some people think it actually is a good thing if these countries have to depend on each other for their water supply, because they'd have to collaborate, and that might be conducive to peace in the long term. Of course, it's a very complex thing. But as I said, our project is mainly about giving students a chance to work together to tackle this problem. So what we have developed at Aston University, which is where I work now. I'm now working at Aston University as a researcher and teacher, is we've developed a technology for the desalination of brackish groundwater, which is actually very efficient. There's a particular issue with the desalination of water inland, which is called the recovery ratio. Every time you desalinate a cubic metre of groundwater inland, you produce also a brine, the leftover salt. You have to do something with the salt. The salt can't just be made to disappear. It has to be managed in some way. So that means what they call the recovery ratio of the system is extremely important. So you want the maximum amount of fresh water out of the system for the certain amount of salt water going in. And our technology can maximise that without too much of a penalty in the energy consumption. It's also very simple, so we've got teams of students in different countries to actually build these systems and get them working, and we'll explain briefly how the system works. So this is an animation of our system. So I'd like to highlight a certain commonality with what I did with Brian in the idea of the reversing flow. This RO module contains the membranes, and this other module contains what we call the pressure exchanger. So a lot of the wasted energy in desalination is to do with the brine, which is discharged from the RO module, contains a lot of pressure. Reverse osmosis as a filtration process operates at a pressure of up to about 60 bar. So it's a very large pressure with a lot of energy associated. So in reverse osmosis, the concentration gradients are actually very important in limiting the performance and determining the energy consumption of the device. They determine the salt concentration near the wall of the membrane, and the salt concentration determines the osmotic pressure, which determines the energy that you need to use. So our technology is about managing the concentration gradients, both in the perpendicular sense, which is called concentration polarization, but also the longitudinal sense, which is sometimes called concentration factor. But both of these problems become overcome by effective recirculation and mixing. So when you dig into the energy consumption of desalination, you actually find these concentration gradients present a bottleneck. And what's happened is, as they've improved the membranes, the pore friction has gone down, efficiencies of pumps and motors have all increased, and the concentration gradients impose an increasing bottleneck in the process. Coming back to what was talked about earlier then about the fluid mechanics, and this is more about work that I think would have scope in the future as far as much as work that I'm actually doing at the moment. But becoming interested in this reverse osmosis problem caused me to kind of reflect and look back at the literature, and I started to do a lot of reviews of papers and found there's actually a huge literature about this, a huge literature. I mean, most of it going back to the times of Brian, most of it subsequent to Brian, about how secondary flows and vortices could enhance mass transfer in this kind of device. So, Ian already showed us these vortex waves, and there's lots of other configurations. I mean, I think this was known about, that was an early idea, which was actually used for hemodialysis or plasmapheresis. at the same time that Brian was working. I think there was a device on the market that was competitive. But there are lots of secondary flow configurations. And in fact, it turns out that in reverse osmosis devices, even by accident, you have people have kind of rediscovered these vortex waves subsequent to Ian's work. If you like, by accident, they maybe didn't call them vortex waves. So what I would really like to highlight is that I think that the kind of things that Brian and then Ian were working on really have a big application today in the improvement and optimization of reverse osmosis devices for desalination. So one of the frontier areas today in desalination is to try to incorporate biological proteins into artificial membranes. So there are proteins called aquaporins that miraculously enable an extremely fast water transmission through the walls of the cells of our bodies. And there are companies now that actually, or there is one company that's actually succeeded in producing a commercial product based on this biomimetic principle. We're developing a collaboration with them. So I think it'll be very interesting, and this isn't work that I've done or anything, this is work from the literature, but it's showing the complex patterns of vortices formed in these devices. It's all been modeled in 3 dimensions now, which I dare say would have been difficult at the time that Ian was describing in the 1970s. So, yeah, so that's my reflection on the work on the vortex mixing and what I learnt with Brian. Just before I actually finish, I just found preparing this lecture caused me to kind of read over my thesis and just refresh my memory of what I did actually do at 43 Banbury Road. And I just found, sorry, let's get on to this one. Sometimes we've heard about kind of blood products and surgeons with knives and cyanide. Did somebody say something about cyanide? It sounded like it might be quite dangerous. But I thought you'd be reassured to know that it was all perfectly safe. So I just wrote in my thesis, since radioactive substances were being used, safety had to be considered. It was undesirable that the equipment should spray the operator with radioactive fluid should a valve fail to open and create a back pressure. Pressing the spacebar on the computer keyboard, this was the same computer that Lionel showed us, I'm sure it was, at any time interrupted the program and caused the pumps to stop and all valves to close. A perspex green was used to cover the main tubes and connections. So there was nothing to worry about, it was all perfectly safe. Except for the paternoster lift in the building across the road, which has been decommissioned since, I believe. So, yeah, so there you go. That's it. Thank you very much.